Good evening. Already I put two videos which are from previous question papers. I have taken around 5 question papers. So the problems which are not similar, that I am going to solve over here. Problems which are already parallel to the revision lectures will not be solved over here. Now these questions are from May 2019. So May 2019. And now in this we have two questions. So one question we have calculated the UDN, laterally unsupported beam. You can have revision lecture 4. And then this is similar to this. There I think we have ISMB 350 and here we have ISMB 400. Now this we are going to solve over here. A simply supported beam of span 6 meter loaded with UDN, uniformly distributed load 25 kilonewton per meter including self weight. Also subject to 2-point loads 50 kilonewton at quarter span from support. And then if compression flange is simply supported, then we have to solve this. So now we have this step 1. So given data. We have given W 25 kilonewton per meter. We have concentrated loads 50 kilonewton at quarter span from both sides, and beam is laterally supported. Laterally supported. Then we have step 2, shear force and bending moment. Shear force and bending moment. Now we are not going to write shear force diagram and bending moment diagram. Otherwise you have to plot it. Then we have, this will be shear force. Sorry, this is beam. We have UDN 25 kilonewton per meter. Span we have 6 meters. So we have two loads at quarter span. This will be at 1.5 meters, 50 kilonewton. Then this second also we have 50 kilonewton, 1.5 meters. Then we have RA equal to RB, that is equal to your shear force, we can say. Then we have symmetrical, so we have total load by 2. Now total load we have 25 into 6 plus we have 2 into 50 divided by 2. And then it comes 125 kilonewton. Then we have M, that is equal to, now this is reaction. Maximum bending moment will be at center, that is 3 meters from here. And therefore we will get M max 125 into 3 minus 50 into 1.5 minus 25 into 3 square by 2. So if we will calculate this value, 125 into 3 minus 50 into 1.5 minus 25 into 4.5, it comes 187.5 kilonewton meter. We have factorial values, factorial shear force 1.5 into 125, and it comes 187.5 kilonewtons. and mu factored moment ultimate. So factored m max or mu 187.5 into 1.5, 281.25 kilonewton meter. So this is main part. Then remaining part we have same. So we have now step 3. Section modulus required. The required section modulus. Then we have ZP required. Mu into gamma mu upon Fy equal to 281.25 into 10 raised to 6 upon 250, and required value is 1237.5 into 10 raised to 3 millimeter cube. Then step 4, select section. Select section. Then we have ISLB 450. ISLB 450 at 640.9 59 Newton per meter, and ZP Z value is 1401.35 into 10 raised to 3 millimeter cube. Now we have value of TW required for shear capacity is 8.6 millimeters. Now I am not going to do this classification of section. Now step 5 first. Shear capacity. Shear capacity. So we have VD equal to FYW upon root 3 gamma MW D into TW. So 250 upon root 3 into 1.25 into 450 into 8.6. And it comes 507.81 kilonewtons. Newtons and 507.81 kilonewtons. And then we have 0.6 VD. So 0.6 into VD 507.81 equal to 304.68 kilonewtons, which is greater than VU 187.5 kilonewton, and therefore we have to use clause number 2, 8.2. Then we have step 6, classification. You have to do it. I will not go for it. And then we have last step, step 7. We have moment of resistance or moment capacity. Then we have MD is equal to beta B ZP Fy upon gamma mu. Then we have this is 1 into 1401.35 into 10 raised to 3 into 250 divided by 1.1. And we have this value 318.49 into 10 raised to 6 Newton millimeter, which is equal to 318.49 kilonewton meter, which is greater than mu max, that is 281.25 kilonewton meter, and therefore self. So we have therefore self, and therefore provide ISLB 450 at 640.59 Newton per meter. So likewise, we have to solve the problems of design. So now we will stop here only. Thank you.